Yeah, I'm ready. We start.
Okay, hello everyone. Today Aziz is going to tell us about homotopical characterization of contextuality. Okay, so I think we can start.
Thank you, Cihan. Thank you, everyone. Okay, let's start with homotopy. I want to remind you the relation between two maps. If we have two maps from the same x to y, okay, between topological spaces, the same space here, x, the same x, let's say, okay. So one can ask if we can move from one map to the other continuous way. So the way to do this, to take the cylinder of this x, right? And if we have such a map from the whole cylinder, such that this commute, it's mean like when I restrict on this x, it will be g, and when I restrict at the end, it will be f. Okay, if we have this, then it's this two called homotopic, and this is homotopic. Okay, of course, we're interested in people at the beginning interested of the maps itself, but also, of course, like this is also a map, the homotopy, which is like higher order map. Yeah, this is the homotopy. I expect like every one of you know this for topological space in top. Okay, this is the cylinder, like it's x cross 0, 1, or I, let's say, call it. Okay. The interval 0, 1, or maybe let me call it even delta 1. This simplex. So same, actually, we know that why is simplicial sets people use. People want to think about topological space in some combinatorial way. So in simplicial sets, we have this phenomenon of homotopy in simplicial sets. So if we have the same, we have some two maps, F and G, from now in simplicial sets. Okay. Again, we can define what is, we have delta 1, right? We have this delta 1. It's okay. You all know what's this. Okay, delta 1, that it's generated by one simplex. In like delta 1, it's have in one generating simplex sigma. Okay, which is the interval. The other, of course, like we have here a point, so S0 will appear, and will appear all the degeneracy here. But this is the one that generated it. And sorry, here we have two, A and B. We have two, it's not zero, okay? And we have S0 of A, S0 of B. And we have more, okay? In the degeneracy, but this is the only one that it's like generated. It's not degenerate. So we have this, and we have a product. The product is so easy in simplicial sets. The product is, if we take simplicial set and other simplicial set, and we take the product of them, so in the end, it will be the product, this product. And everything is appear here. The reason actually that the product is that simple, if we compare with the product in for simplicial complexes, because of the we add this degeneracy map. Like we add for everything, we add a presentive of this in the higher order, right? Like even we have like in y here, y1, we have like this some edge here, but this edge also will be triangle here in two ways, right? And will be also a pyramid, and will be, right? So this is the reason, if you think this is the reason why the product really is this. And if we go to, the realization of simplicial set, when I think about simplicial set at topological space, the realization of simplicial. So we have this important thing that if we take simplicial sets, we take the realization of the product. It's exactly to do the product with topological space, to take the realization before and then to take this. So the product will define. So that's why we can define here also the cylinder in the same way by taking this delta 1. Or maybe it's some people will call it like this delta 1 in order to, yeah, it's not, this is topological space, this is simplicial set. So if we take this, here also we have two inclusions, like like here we have two inclusion to the cylinder, and these two maps are homotopic if and only if we have such a map f that makes this diagram and this diagram commute. Okay, so the same we have this homotopy in the in simplicial sets. So this homotopy relation between maps in simplicial sets. So let's now, maybe you have to move now the camera, or it's not like this, it's moved by itself. Maybe new one I need here. Which one you mean? Is the red or the okay. Really? Now it's better. This is better. Yeah. Okay. Okay. So let me just, I want to show what happened to one, like if we have just one map for one edge, like this is a simplicial, you know what I mean, like delta one. Okay. This is delta one, or the realization of delta one. Now I will write it like this. Okay. If we have, what is like delta one cross delta one, I mean, what is delta one, how it looks like. Okay, I will not going to show it by detail. You can find it in this known one for Friedman, for on simplicial sets. So it will be like this. Like if we take this delta one, like this, I use here delta one twice. Like this delta one, I mean the x, my x. Okay, this delta one in order to take the cylinder. So I have two copies of this here and here. So we need two triangles here that related between this. Okay. So, and this is homotopy between this and this. Of course, like if you take, now I want to, okay, this is delta one. I want to take maps to some source. I will take this, the nerve of Z2. Okay, we can take the nerve of Zm. Why the nerve of Zm in general? Like it's have something not homotopy, because we know that I will not talking about the representative of this as topological space, but let's say that we know that the pi one of this is Zm. Okay, so let's take Z2. So what that means, that we have some non-trivial circles. Okay, yeah. So we have some non-trivial circles. So let's take a circle. Let's take this circle like this. Circle like this. I mean here simplicial sets, but you understand we can like find simplicial sets which is generated by two simplices. Okay, glued like this. Yeah, like you can think topological space, like it's only like a graph, right? You can think about, but in simplicial sets, like we put it in now, like we put here, we have one dimensional, this is one dimensional, and we have 0 dimensional here and 0 dimensional glued together. So we can say, okay, this is sigma, this is tau, so we have sigma and tau, and we are A and B, and so we write here in the 0, like here is the 1. A and B, okay? So we have only this A and B, and we have here, and you have something that says that, okay, the edges of the first, the beginning and the end of this, what is the beginning? So you can have maps here that tell you what is the end and what is the beginning, D1 and D0. So like for example, this is sigma, D0 of sigma, it's when you omit this beginning, so this is 1, D0 of this will be A. Yeah, and for this, when you apply this is a map D0, and this will you give B. Same for this tau. But you are, it's not the way to, there is also degeneracy. Okay, okay, I will not go towards this. Okay, we have more like, but it's only to make the theory good. For now, we don't need this. But okay, if we have now a map to the nerve, of course, we have a map to the nerve of Z2. Let's take the nerve of Z2. This is not good, you said, right? I was using the red, yeah, sorry. So to the nerve of Z2, we want to go. So now the nerve of Z2 have some null homotopic. Like I can choose here map that some trivial map like this. This will be trivial when I put. You can think about this. Here's a nerve. I just want to remind you. This one, it will be a point here, and Z2, and then Z2 cross Z2. So in order to choose a map, we need only here to put number for this and number for this, right? And this will be agree here because there's something unique here for simplicial map. If we think about simplicial map, so okay, so we have like I can choose this is one map like 0, 1, and the other map 0, 0. One can see that this is trivial, and this is not like we can. There is no homotopy between these. Okay. There is no. Well, let's show it. It's easy to show that there is no homotopy. So you understand that a map from an edge to nerve of Z2, it's easy because there is nothing there. So it's only to choose numbers from Z2 to this. But for a triangle, you can do this as exercise. Like if we have a map from triangle to nerve of Z2, so you have to choose in numbers. It will be good exercise, a number, but such that if this is the number x, let's say this is number y, this have to be x plus y. It's not important the direction. Okay, this can be good exercise. Why? Like a map from a triangle to nerve of Z2, this have to be the sum, have to be the third one have to be the sum of these two. Okay, there is a rule, of course. For Zm it will be a little bit, but here because the minus and the plus the same, it's work like this. Okay, so let me show you why really we can't find the homotopy in this. So I will write the circle like this. I will write the circle like this because it's easier for me than I'm not good the drawer. I can draw it like this, but it's a start and it at the same point. Like this is x the point or A, B, but here A. This is a circle. Okay, and this is another circle. The same one. And let's say we have here the map 0, 1, and here's the map 0, 0. And I want to show you that there is no homotopy between them. Okay, so I will write, this is the cylinder. Like we said that if I take this edge with delta 1, this will be these two triangles here. Okay, and this the same two triangles, but of course because this is the same edge, this will be the same as this. Okay, this one is the same as this, so it will be cylinder. Yeah, cylinder. Yeah. So, and let's see how we can put here something that to get this. Let's start like by putting here 1. What I can put, or 1 or 0 in the triangle, right? So if this is 1, so because I know this is triangle, this will be the sum of them, right? So this will be 1. Because this is a triangle, this will be the sum of them, so this will be 1. Because this is a triangle, so this will be the sum of them, so this will be 1. Because it's triangle, this will be the sum of them, so this will be 0. But this is the same one, right? So we can put here 1. But if you also started by 0, you will get also contradiction. Okay, so there is no. It's easy to see that there is no homotopy between this map. Two maps is not homotopic. Okay, so this will be like this will represent the non-trivial here in like because it's Z2 for Z2, so there is one non-trivial. This will be the one non-trivial, and this is trivial group. But now, how it's related to simplicial distribution? Here is the question: how it's related? Actually, because we can think. I move. Okay. You moved. Yeah. I remember when you give me this to control this, I was forget all that. I was forget all that. Yeah. So we can think about every map as a simplicial distribution. We think what is, let me show you. Like if we have this x to y, we can go to the distribution on y, right, by taking delta. Like this will be mapped by 0 and 1, right? We have this delta y, and we can go to this. The same if we have such a map f, and we have other map g, y, we can go to lambda y to this y. So this is the same map actually, is in same information, the same map here. But now we can ask, okay, what about this? Like, okay, this going to the cylinder, but we know that if we, just a minute, we going to the cylinder. Let's say this maps, what we have there. This is not homotopic here, like if we going to the same y here. There is no map like this that makes the diagram commute because it's not homotopic. But what about if we going here and we allow simplicial distribution to do the homotopy? Because this map now, we think about them like this. Can we have a map like this that make this diagram commute and this micro commute? Like if we think about them, that the what is the co-source, so the what's called the, it's the distribution on y, not only y. Like we extend it ourselves. What about this? Can we find this? So let's do this example, and I will show you that really we can do this. Back to the example. So the example A, B here, A, the same A. Here's the same one we said, right? And we have two triangles like this, and this is 0, 1 here, and this is 0, 0. Okay, 0, it's what it's mean like 0. Now we think about this as a distribution, but we can still write 0. What we mean, like this is a distribution that for 0, it's 1. The distribution is 1. In 100%, I got 0. And to get 1, it's 0. It's a little bit, here we mean the number 0. But here we mean the distribution, like the probability. Yeah. Okay, here's the opposite. The probability to get 1 is it's 100%. Yeah. So, and we here we can put distribution, and you remember the distribution on triangle as we explained, like we can put here p1, p0, 0, p the one for okay, it depends on the direction, so I'm not care about the direction now, but we can put like this, and here p1, 0, right? We can write like this. So it will be a good exercise to show if we have, because I will show you some distribution, but this will be the unique distribution. So in order to prove that it's a unique distribution, one should do this from the beginning. I will write this distribution. So it will be 0, 0 here, because I want here to be no, actually, this means that to get 0, it's half. So I will put here half, half. Like it's 1 to get 0. So it will be, okay, half, half. I will put here 0 and here 0. So this is the distribution of this. Here again, half, half, 0, 0. You see here, the same. Like we said, we have to be the same here. This is the sum of this 0 and the sum of this 0, because this is the distribution on this. Yeah, half and half. Sorry, here half, half. So, okay, can continue here. Here is also 0, 0, half, 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 0. Sorry, half, because this is 0, like it's mean like 1 to get 0. So I put here 1, yeah, and here 0, 0. For this one, because it's 0, 0, because it's to get 0 is 0, the distribution, and here half, and here half, and we see like, okay, everything is the same here, like this for this one, here it's half, and here it's half. Even for this one, yeah, here it's half, and here it's half. Yeah. So this is a region. Actually, this is the unique one, the only distribution that you can. It will be good exercise to show this, that this is the only one. But if we,
Is the notation clear? We have 0, 1, it means delta 0, delta 1, right?
Yeah, here delta 0. Yeah. It's maybe better. Yeah, right. Yeah, you are right. It's better to write it's delta 0, delta 1. Yeah, because the same we sometimes write 0, but it's delta 0. Exactly. Good. So we see that this is it. But if we think a little bit, like, what is this scenario actually? This is scenario for triangle. And we know that when we use the nerve, then the edges will be the measurement. So we can say that here we have, actually I need another color now, but let me know if it's good, because otherwise it will be, I already used here E and B. How we can use, you remember that, let's call it X and Y, because you remember it's by A and B, Alice and Bob, right? I think this is X, Y, X. You remember Alice and Bob, that Alice have 2 and Bob have 2, right? 2 measurements, and they all together, like I have a context between this and this, between this and this, between this. So here, this is a context, like if I call it A, this the one measurement for Alice, and this for Bob, and this is the context, and here this is again A, the other A tilde or A tag. So, and this is B, and this is again A. With the direction, it's not important, like it can be also. Okay, anyway, but you see, like this is exactly CH, this is present like this one with the nerve of Z2. Yeah, like this as a space, I mean, without this number, what I wrote. This is exactly the CHSH scenario, it's represent, right? And this distribution, the unique distribution inside, this is the PR box. This is PR box. You know PR box? You didn't? This is extreme point. You know vertices. Already we talked about vertices. This is one of the vertices. There is 8 vertices. Okay, all similar, like this half one, or similar like this. There is 8 like this. 8 half. This is one of them. Okay, the CH, and we can get all of them by this, by doing a homotopy. All of them will be homotopy for some maps that it's not homotopic in the real world. Okay, so interesting. So, but it's get like the homotopy, and it will be the unique, and it's contextual vertex. So why it's true, and yeah, here one can ask why it's true, like why we got that the homotopy is a contextual vertex. So now I will explain. Okay, we will start. This was motivation, and we will explain now why this happened. It's no, it's not a coincidence. No, it's really, there is a reason for this, and there is something general. So let's start by giving the definition of strong contextual. What it's mean to be strong contextual. You know what is the definition of contextuality, but what it's mean more strong, it's of course it will be something more, like if every distribution, that simplicial distribution that's strong contextual, it's of course contextual. But what is the definition? So first of all, I want to define the support of, now something general, okay, given simplicial scenario xy and p simplicial distribution there. We will define the support of P to be all the simplicial map from X to Y, such that we will have the following thing, like P, if I take P on some X, like X is some simplex on X, okay, well, I can write like this, but we always write, sorry, Pn X, maybe I have to write, but we write like this. If I write this and put inside this phi x, because phi x, it will give me something on Y, right? So Y, it will be non-zero for every x on xn, like also n is general, and then it's any number for every n. Okay. What that mean actually, like let me maybe show you some example what that mean. Like if I have, for example, a distribution like this, we can write sometimes a distribution, maybe like what we wrote here, like triangle. Like I'm writing quarter, half, quarter, 0. Okay, and I will take phi here. It will be, for example, on triangle also 0, 1, 1. Yeah. So 0, 1, 1 as a distribution, one can write it like this. As a distribution, one can write it like this. This one, 1 here. So it will be, I want it to be 1 in this side. For the 0, it's 1. I want it to be 0 here. So I can put here, what? Just a minute, sorry. I want here, to be 0, 0, like the 0 to be with distribution 1. So this one. Yeah. So that means like the distribution to get, yeah, like here in the arrow, it will be delta 0 here, delta 1 here, and delta 1 here. So yeah, so the distribution to get 0 is 0 here, the sum and the sum here. So we see like that this is really in the support, because everywhere like if we put the phi x of this, what is like this is x is a triangle, and if we put the order of value, let's say like this place is the 0 1 place. So if we put here the 0 1 place, it will give me 0 1. But if we put here the 0 1 place, yeah, it's quarter, it's not 0. Okay, we can see like this. Like if I'm now taking this, something that represents this, so this will be not in the support because here is 0. You can think about this like this. It's easier. Yeah. So look, in simplicial distribution, like when we have non-contextual distribution, like it's mean, like what it's mean, non-contextual distribution, it's mean we have this theta, you remember, this theta from the distribution on this, on maps like this to here. Yeah, to here. If we have some p here that coming from something here, some q. So what is q? It's some distribution of this. So in fact, this means that p, it's a mix, some a convex mixture of what of some deterministic distribution. Like we can write it's like alpha 1 of delta phi 1 plus alpha 2 of delta phi 2 plus alpha, for example. But this means like this is 3 are in the support of this phi 1. Thank you. That phi 1, you can prove that then in this case, this 3 of this are in the support of, they support P. This is much better. Yeah. Yeah, we see, one can see this. It's really not hard to show this. It's by definition actually. But sometimes we have something that here that like some Q that not coming from these anything here, okay, which is mean contextual. But still there is something in the support. Yeah, like because I can write this Q maybe not as a mixture of this, maybe I can write it's alpha of delta some phi, and then the other something that it's I can't find something in the support. Yeah, so it can be. And sometimes you can't find something like this. It's not anymore in the, okay, it's as a support. Like the support is empty. We called it strongly contextual. Okay. So definition. P is strongly contextual. I will write like this in strongly contextual. If and only if, okay, this is definition. If support of P is empty. Nothing support of P, okay? So of course we know that if it's strong contextual, support is empty, so we can write it as a mixture, so if it's contextual. Now, in terms of the BilTop things, already Salman talked about this BilTop because we know that all the simplicial distribution together form a BilTop, right? You know, of course, when we take x to be finite generated and y. Anyway, like in general, like our example, it will be BilTop. So let's say this is I will write some picture, like of course it's not the picture, the good picture, but where was I? Okay. Like let's say something like this. We have I did no, sorry. Okay, anyway, like here is this. I mean, here every point is simplicial distribution. All of them for BilTop, of course, large BilTop, but this is only some picture like this. Maybe it's not good picture, but anyway, like this is the vertices here. Like what it means like to be a strong contextual. Like here, for example, this is not a vertex, but this is a strong contextual, or this. Why? Because I can find this as a mixture with something. Okay, maybe it's not in the definition, but one can prove that this is really the same. I can find like this here is a deterministic distribution here, and the convex of this inside this all the non-contextual. But here, like this one, for example, is still like this is contextual. The red, all the red is contextual. It's outside this, but still I can write it as a mixture of this and this, right? I can write it. So a mixture, I involve something deterministic, but for this I can't. Yeah. So this is strong. Everything's here and everything's here, and this one and this one are strong contextual. All of them. Yeah. So this is what that means in picture. So let's now show why really this is right. Why we get that this is right. So let's show is in general, like why we got this. We see here that there is a related a little bit between contextual vertex and strong contextual, right? Like every contextual vertex by itself is a strong contextual, right? But not the opposite, because this one, it's not a vertex, but still it's a strong contextual, okay? Like the opposite is not true. In the CH scenario, actually, is the same because we don't have other strong contextuals that not contextual vertex PR box. So let it prove this is true. We can take this map X. Here I mean that this join union, okay? This join union, this map to X cross delta 0. And because of the naturality of theta, this will induce square, the following square. Actually, this will be up. No, this, okay. Two or m or any like it doesn't have to be. Okay, this is the theta that corresponding to this one. Yeah, and there is the one, the theta that corresponding to this. Something wrong here. Yeah, I forgot this here. Why? Sorry, x as x. Now it's right. Okay, and we have like this, there is natural, so this map, it used to map from here to here, right? Like this is I, so this map, we can call I. Delta 1. Yeah, delta 1. Yeah, I wrote before delta 1, right? Or I always don't. sorry, delta 1, of course. Of course, here also delta 1. Yeah, thank you. Yeah, delta 1. The interval, we mean, sorry. So here we have a map like induced by this, and here we have a map induced by this. Anyway, so we have this commutative diagram. So from this commutative diagram, we can get this, what we say, the strong. Let me explain a little bit. So if we have some P here, what we said, like we have, if we have a homotopy for something, not null homotopy, like if we have pair here, because actually a map from here to here is pair of maps, like because it's from the limit, from the co-limit, from union. Like map here, it's two maps. So phi and psi, let's say. So this phi and psi give me here in, if we take, now, of course, I mean delta of phi and psi, of course, like here, because I want to think about phi and psi as a distribution. So I will take delta, the delta of this. So this will give me a map here. If we apply this, just a minute, yeah, delta of p of psi, yeah, this will give me, actually, if we take this like delta, it will give me also like something like delta of psi, because it's like unique here in this is sorry, like identity here. Okay, like when we take something from here, there's two meaning of delta, actually. Delta, when we go, it's a little bit confused, but try to understand me what I mean. I mean, like we have from here, actually it started these ones. Let's take now the pair here that it's not homotopic. Okay, pair. So this will give me a map here, and exactly this will give me some delta of this, something like this. So let's say that we have a homotopy for this. Let's say that we have a homotopy that going from this is simplicial distributions that make a homotopy. So this can't be have a support. Why? Because if this have a support, something like here that support, okay, one can prove, it's, yeah, it's need to work. I will not going to prove now this, but one can prove that this will be, I already used psi, maybe I will use another things like something like this, like it here, in here that supports this. If something from here supports this, then it will be a map that this map will going to this, or to this, to this one. What it means to this one, it will be homotopy between this one. If you think what it means, that some extension of this is X, the union, and some extension to the this is exactly homotopy. Yeah, but we talk something that it's not homotopic. This is the idea of the proof. Okay, I'm not going to do this in details, but this is the idea that if something here in the support of this, then this will be a homotopy between these maps. So we don't have, and yeah, we get this general that if we have something that not homotopic here, and we going here, and if it's have a pre-image, then this pre-image is strong contextual. But we can say that if it's the unique one, then it's contextual vertex. Because of this, one can think about this picture, like, because this give me all the facets, like all the pre-image of this, if these are not homotopic, all the pre-image, maybe we have another, all the pre-image together give me facet like this, face like this, or face, yeah, give me this one. If this unique, the only pre-image, then will be like this, contextual vertex. Okay, so this is the thing about homotopy. But let's say what is the problem here, and what is, or maybe let's say why it's not general. Okay, it's some good observation maybe, but it's not general. What is the problem here? So first of all, like this, what is our scenario? that we detecting, we use this in order to detect some contextual vertex. Which scenario? This scenario. In this scenario, not in this scenario. No, in this scenario, right? We talk about simplicial distribution here, which play the role of homotopy here, like something that it's not having something to relate, like higher order map to relate between this map, but it can be here, then it will be strong contextual. So we are working here. Yeah. We are working here and we can detecting some vertices here, but the thing that this not represent everything. Like I can't give you some like for you know the some scenario. For example, this scenario, two observer, three measurement everyone. Yeah, if we have two observer, three measurement everyone, this can be represented by this, because this is something. Yeah, x cross delta one. Delta one. Yeah, I don't know why I put always the time delta zero. Yeah, delta one. We can represent it by this. Okay. Yeah, like many things we can represent it by. Yeah, M arbitrary can be. Yeah, here M anyway, but no, I mean here is the problem. It's M. It's not a problem, but this like to be with two observer, Alif and Bab, and this one have three, and this have three. So we can't like this, for example, but we have many examples like this that we can't really represent this by this. So it's like some kind of not everything, some kind of what is actually is it K33 or anything? If you take anything, you can represent this. No, K33 not represent. No, here we means exactly. That's why you. This is why I'm writing all the time. You maybe. No. It's not. We don't. Yeah, this is why I'm putting this delta zero, because I'm long time we didn't talk about this delta one. Yeah, it was a beginning like this, and then we found that okay, we can't, like not every, it's not flexible. Yeah, not everyone can represent it. The other thing that this map, let's say like call this map I star here, that I star not surjective, maybe not surjective, we don't know. Yeah, we don't know if really always we have such things. Yeah, maybe not surjective. So this is two problems that it seems like we need to change a little bit, or to think about something else. So let's now we said that there is our outcomes. It can be the nerve or delta, right? Delta of Z M. Like we can do these things. Like you have to remember this. If we want to, we can take our outcome space to be delta Zm or nerve of Zm. In this case, the measurement will be the point, and it's related together. And in this case, the measurement will be edges. As we said, already we only work with this. You know what I mean? Yeah, the measurement here represented by A, this is A, B. But here no, B, A prime, B prime. I don't know, there is more measurements. So this is a difference between this and this. So, but let's do what we did here for delta Zm, because if one notice like this is have related with this. This have some relation, have homotopical meaning, this delta Zm. Okay, so let's talk about the meaning of delta Zm. What is the meaning? Like before we did the homotopy by X, like because homotopy, one can do the homotopy relation by the source or by the co-source. Let me remind you this point. Okay, let me go there and remind you this point, and we can go and see what I meant there. Like how to define, how to say that two maps Actually, we can using the cylinder, but we can using also the path. The path, yeah, I don't know, you know about this? Like we can using in order to say that this is this map are homotopic. We already say this, like okay, by going to the cylinder, right? This is x. We have a map like this, but we can say something else. We can say that we have here the opposite of this. We have two copies. We have here the how I can call it the sorry 0 1 y. This one. This is what is this? This is I mean here the interval 0 1. Yeah, this is x cross 0 1. We can do this, and this have two projection like this. What is this? This is all the what it's called this path. Yeah, all the path on y. Yeah, and we have the end point, one projection to the end point, and one projection to the the beginning point. Yeah, the initial point. Yeah, one projection. So if I have two maps like this, f and g, so these are homotopic if and only if I have unique map to the path. Yeah, like we can see the homotopy inside y also. This is the dual. Yeah. Yeah, it's a joint. We will talk about this. Yes, this is the dual. So here we have y. This is y. This is x. So we said, okay, f may be taking this, but there is a path always between the values of x to the values of g. What it's taken, there is a path all the time. If it's yeah. So this is the dual definition. And but we're interested in null homotopy. So how we can define null homotopy in both? Null homotopy, the map is null homotopic if it's homotopic to a constant map, yeah, null homotopic. So we can define it using the cylinder. Like now we map one map. It's not homotopic if it can come through now the cylinder. Like this is x. This is what called the cylinder of x. If I can find a map like this, and this coming through the cylinder, that means that it's continuously its contents. Okay, like I put here, instead of saying that it's homotopy to the some context here, yeah, I can say this, right? But we can do also the dual of this. What is the dual of this? The dual of this is to take the path that end at one point. It's called py. Py, what I mean by this? This is all the path inside y that end or the beginning of this, it doesn't matter. Like let's say that for our things we need, I think, the beginning of this. Okay, anyway. Yeah, the end it's one point. There is one point, fixed point on y. Y is pointed. So that end in the first point, and we can now like define this. This is null homotopic if it's coming through. There is a map now from we have project from this to this, right? From py to this, that every something here going to the first point, yeah, like here some phi going to phi 0. The end point, it's always the same point, but here phi 0. And if we can extend, this is a dual of this. If we can find some j that makes the diagram commute, that means that this f is homotopic to point to contents map. Okay. It's this is the dual definition of this. So how it's related to this delta Zm? Actually, this delta Zm play the role of this. This is called actually the path also. But I mean, when I mean by this, the path that end by what fix on one point. Okay, all the paths that we fix one point, as all the paths that fix the end of them the same point, in the same point. So this one represents this. You can think a little bit about the. Okay, let me give the general definition, and then I can relate to this one. So the general definition, what calls the declarage, let's given definition given y simplicial set. We define clearage of y. It's easy how we define it. It will be in the n place what it was in the n plus 1 place there, and we omit d0 and s0. What I mean by this, let me explain. Like, for example, let's do this for the nerve as example. For the nerve, what is the nerve? The nerve is this. Z, here we have Z, here we have Zm, here we have Zm cross Zm. This is the nerve of Zm, right? And you understand what is the maps from here. Here there is what is D0 and D1. Here it's obvious what is D0, but here, for example, from here to here we have 3. Like we have D0 by omitting the first one, and D2, and we have D1, which is the sum of, right? Is the sum. And here we have D0, it's also by the first one, and D3, but we have 2 like by sum of this and this, and taking this like sum and identity, I can say. And here we have D2, which is identity and sum. Okay, you understand the rules here. But if we take now the clearage of this, what they're saying that, okay, in the 0, like the point will be the edges, yeah, the path, like our element is the path, yeah. So this is the idea why it's but in some, so it will be like the one here, the 0 here, it's 1 here, so this will be this Zm, and then Zm cross Zm. But from here to here we have 3 here, so that's why we omit this one. Okay, so we have here only D1, which plays the role of D0 now, and we have D2, what we have before, which plays the role of the 1. Okay, the new one. Same, we continue, and if we omit, same for the degeneracy map. I'm not doing this, but it's the same. But we see that this is something similar to delta Zm. Let me remind you what is delta Zm. Delta Zm as object is the same, right? As the sets is the same, but a little bit there is different between there is a difference between these maps, because here this maps is to delete the first one, this map. No, sorry, this one to delete the last one, but this map is the sum of them. Here, this map, the last one is to delete the last one, but this is the sum of this, and this by taking the sum of this. But here, no, all the faces map by deleting, and all the degeneracy map by copy. Okay, this is only deleting and copy. There's 2 ways here to delete. There is 3 ways here to delete, and this will give me the faces map. But you can find isomorphism from here to here. The isomorphism, it's I wrote a formula because there is, of course, from here to here and from there, from both. This from this, like this is delta Zm, and this is big of nerve of Zm. So by going A0, A1, like in some place here up, this one, AM, this is going to the A0 plus A1, right? Yeah, A1 plus A2 until AM minus 1 plus AM. Yeah, it's going this direction. And of course, like from here to here, one can find the formula. I think it's by sum all of them. Yeah. Anyway, so this is isomorphism between this simplicial set. Okay. So what we can say that this delta of Zm plays a role, delta of Zm play the role of the path space of the nerve of Zm. And because like from the declaration we have some map, like as we showed there, like we have this map. Why also we have this projection here from the declaration of this, which is delta of Zm to the nerve of Zm. Okay. But now it's I'm doing the opposite. Before this, what we had before, we had before a map from this to delta 1, right? And by this we got square, but also by this we can get square. Let me write this square and discuss. So we have here of delta Zm, simplicial sets from this to this. We have this map. Yeah, and here also. We have here theta of this like x delta Zm, and we are here theta for nerve Zm. Yeah. And this diagram commute. And the same thing we can do here, what we did before. We can say like if I have here a map here, like coming from here, see that it's not homotopic. What mean it's not homotopic? That it's not coming from here. Forget about D, it's not coming from here, right? It can extend as we say there. Like it can, this is x to the nerve of Zm, and we have this map, this projection, so it can't be extended like this. There is no extension like this. That means it's not homotopic. So because there is no extension like this, everything we can go like this phi when we're going to this delta phi, and when we take some pre-image of this pre-image will be strongly contextual. Okay, this pre-image will be strongly contextual. What good here? The two problems that we had before now solved, because we now talking about this scenario, and this scenario can be anything. Yeah, this every Bell scenario and more, and this flexible. Yeah, this delta set. This is good. The other thing, this is surjective. Yeah, this is surjective. Let me write why is this surjective. There. What? Yeah, split. Exactly, split. Yeah. Exactly. Actually, let's compare between. This is the thing that when we have this delta Zm, which is the declarage of this, the path, and this is nerve. This is contractible. This is a projection, okay, but without any split. There is no any split. This is some projection of topological space or simplicial sets. But of course, there is no split because this is not contractible, but this is contractible. Like this is the things, like what it's mean to have the cone, like to be null homotopic is to going in topological space to go through the cone, but it's to go for anything that is contractible. It's enough, or in the opposite side, yeah. So that's why the cone and the path, both of them are contractible. The path space. So this is contractible. So there is no section. But if we apply D on this map, like let's call it map pi, or D0, it's called, I think. Yeah, D0. Okay, pi anyway. So D of pi still surjective, but for the reason that it's really had there is a section for this, yeah. And you can find the formula. It's maybe not the time to write the formula of this section, but you can find the formula of this section because we extend ourselves here something, yeah. So there is a section for this. This section induces section here. One can see this induced section here. But even this section have good properties. So this section, it's first of all convex, because we talked about convex sets here, about polytopes. This section will be convex here. Plus, preserve product. Do you remember the product we have? Preserve product. Do you remember the product we have between simplicial when we talked about, yeah. So this preserve product. And this is good because we have more. Let maybe write now this result, what we have. So proposition like we can go from here, everything here. This is a group, by the way. One can see that because this is a group. So this will be group. So this is a group going by this, but this actually, for this map will be inclusion, homomorphism, and this inclusion. So we can say that this group is appear here in this, what is this? Monoid. Okay. So we can write that simplicial set X of nerve of Z M, it's up. Okay, it's not the same unit, but okay, it's a group inside this monoid. Yeah, inside with delta Zm. This inside this, like everything here represents this, represent one here, which is their pre-image. Yeah. Okay, everything here represents this, such that if P it's not null homotopic, then the one that represent is strong, strongly contextual. Then like phi going here to some, let's call it P, depend on phi, let's call it like this, then P phi is strongly contextual. Yeah, so this really appear here, and this is important group here. You want me to define the section? I will define. Okay, we can define. It's not that formula. Yeah, this section you mean? Here, this induce this, right? This section induce this. But how we can define this? This. Like by going, there is a map from here to here. Like this is phi. You going like this to here, and you then apply the section. Then this is what I call P5. Yeah, I can say mass back to. Yeah, there is other maybe P that going to the same phi. There is other, but this is this one. I mean, yeah, this one appear here because all of them form a group there. Yeah, form a group there. Some, yeah, but there is other, of course, like there for everyone here there is some facet here to that, or the pre-image of this, all of them strongly contextual if this is not null homotopic. Yeah, all of this is, yeah. So you want me to continue, or maybe we can stop now and I want to talk about the opposite direction because it's no time, I think, to just to write it. I don't, there is the opposite direction now. Yeah, exactly, the opposite direction, and there's, yeah, well, maybe because I'm here also next week, so maybe I can do this next week. Yeah, so if you want, yeah, we can do this next week. So yeah, better than, yeah. Of course, one can ask about the opposite directions. This will what will come next week. What about is every strongly contextual? It's coming from something like this. It's related to something. Some map is that not null homotopic. Yeah. We will talk about this next week.
Okay, very good. Any questions?
Yeah, it's I know it's not maybe a little bit too much obvious, but maybe if you start to read this paper, I think it will be more clear.
Did
Yeah.
you start the homotopy paper? No. This paper, yeah, the title is exactly.
No, you read about convey. Yeah, yeah.
No.
There is part of homotopy at the end. Yeah, yeah.
Yeah, I think the first picture you.
Yeah,
showed,
maybe.
I
Yeah,
think
yeah,
it was
yeah. It was.
paper
Yeah.
you were looking at, right? I have actually a question about this diagram. So the the top right corner is, I'm not sure if that's the same section, but I think there might be a twisted version of the same kind of argument, because the right hand side you can see that there are other sub things there, sub distributions, or maybe I should say subset of distributions that are
going to the same one, or you mean?
Yeah,
the pre-image.
So the right hand corner, right downstairs, these are twisted distributions on X cross nerve Z mod M, right? So if you think of it as a trivial bundle, so these are twisted distributions on that bundle. Just think of it as a bundle scenario. And any twisted distribution, if you take twisted bundles too, it will be a sub thing of the right hand corner. And maybe you can also find the vertices of those things as well.
Yeah. Okay.
Yeah, I don't know. I mean, that's because there's a natural map that includes. Really? Yeah.
We can talk about.
So there might be a twisted version of this. Yeah, we can discuss that, but I think it's interesting. Okay. Okay. If no questions, let's thank Aziz.
Thank you, guys.